No, that's dynamic head. So yeah, you're right, Cam. So static heads are really simple. Static head, no. The best way to think about it is the gravity that the liquid needs to overcome. Well, it's more, you're very close there, Michael. It's actually the difference in the height of the liquid in the two tanks. So because that dictates the amount of gravity. So gravity is interested in where the top of the liquid is. So if liquid is 2 meters above the bottom of the valve in a tank, there's 2 meters worth of pressure pushing down on the liquid going through that valve. So if we had a tank, and I think we all know this from various times in our life, if we have a tank where we have liquid in 2 meters high, and we have a hose, let's say the hose goes from the bottom valve up to the top of the tank, we open that bottom valve, water will go up as high as the level of the water in that tank. That's due to the power of gravity pushing down on it. So the static head is the difference between the height of the water in the discharge and the height the height of the water in the supply tank or the wine, it's where it's coming from, and the height in the discharge. So people often go, oh, it's easy to pump, let's talk about wine. We need to move wine into a tank and the tank's 2 meters high. It's easier to pump the wine over the top of the tank rather than push against the pressure of the wine from the bottom valve. Well, actually, it makes no difference because the pressure has to be overcome whether or not it's forced into the bottom of the tank or it has to go up against gravity over the top of the tank. It only matters where the height of that liquid is. So the static tank, crucially, is the difference between the height of the liquid in the supply tank, sorry, that should say liquid, and the height of the liquid in the discharge tank. So that's the static head. It's the difference between the height of the liquid supply tank and the height in the liquid of the liquid in the discharge tank. So if I did a really crappy example here, red being the height of the liquid, the static head is actually just this distance here. And as the height of the liquid increases, so say we're pumping from here to there, well let's say it's going from the bottom of that tank into the bottom of this tank. As the height of the liquid increases in our discharge tank and drops in our supply tank, that static head will actually increase because the difference in height will increase as the height increases in our discharge tank and decreases in our supply tank. So when we talk about static head, we always have a minimum and a maximum. And this is all detailed very clearly in the notes. So that's our static head. Static head's pretty simple to understand. It's measured in meters. And it's the meters, effectively, of the vertical column of water. So it's the amount of pressure that needs to be overcome, equivalent to pushing water vertically up into the air, or how much pressure a certain height of water will be exerting on something on the bottom. So that's our static head. Our dynamic head is what, Guy, you alluded to, and that's the friction which is resisting the movement of the water due to everything between one tank and the other. So that's friction of the pipe or hose. Friction due to any fittings. So if you imagine when water has to move around this 90-degree elbow, this here will actually slow the water down because it has to hit this sidewall, become turbulent, and then move to the right. So that slows everything down. If there's fittings, if they're partially closed, obviously, if there's valves, if a valve's partially closed, that will make it a lot harder for liquid to pass through them. Let's talk about fittings that reduce the diameter of a hose. So here we have, let's say, this end of a fitting is 3 inches. So the fitting is what we connect two hoses together. And let's imagine we're connecting a hose with a diameter of 3 inches to a hose with a diameter of 2 inches. Having to force liquid down into this narrower gap causes all sorts of turbulence, and that slows it down. That causes friction. This is all adds to what we call the dynamic head. So the dynamic head is the sum of all the contributors of friction. And we actually measure it in meters head as well. So what we're saying is all this friction, how much does it effectively mean we have to push, how much extra pressure do we have to apply to this liquid? And we talk about it in how much effectively do we have to push that liquid up vertically. So the longer a hose is, the more friction due to that hose there is in the system. The more fittings there are, the more friction the fittings will cause. The more closed the valve is, the more friction that will cause. So we can actually calculate the static head very easily by measuring the difference between the bottom and the top. No, the dynamic head is added to the static head to get our total head pressure. Very good question. Static plus dynamic. So in the notes, topic 3, pump calculations, it goes through all the calculations which are undertaken for working out static and dynamic head. Then, to make life extremely, and let me have a look here. Static head, no problem. Dynamic head. Here's a good example of why I've supplied a spreadsheet for you to help you calculate dynamic head. Because dynamic head is actually the friction coefficient multiplied by the velocity of the liquid squared divided by gravity, which is 2g, 2 times gravity. So that looks actually absolutely horrible, but it's actually really simple. Let's start with the easy one. Gravity equals 9.8 meters per second. We know that. Velocity just equals essentially the flow rate of the liquid. And that's explained in the notes, such as how quickly is the liquid moving. Friction coefficient. So the gravity and the velocity, that's easy enough. The friction coefficient, that seems a little bit ugly. Fortunately, there is a very, let me say, step-by-step linear method for determining the friction coefficient. And remember, if you have read topic 1 notes, we talk about the friction coefficient. If you have to push a box along a concrete floor, that requires a lot more force than pushing a box along a conveyor belt with nice greased up rollers on it. It's the same thing. And roller coefficient of like 0.001, it actually takes 0.001 times the force, less energy to push a box along rollers than it does along the ground. So the friction coefficient is just a multiplier we use to tell us how much extra pressure needs to be exerted on liquid to overcome the friction in all the pipes we're using to move a liquid. And as I said, it's a very step-by-step linear method for determining this. The notes will detail in a step-by-step fashion how you determine the friction exerted by different fittings in a hose system. How much is exerted by expansion valves and reduction valves? How much is exerted by reducing or increasing the size of the hose diameter, as well as how much friction is exerted by different types of pipe. Stainless steel versus plastic hose versus rubber hose. That's all put together to generate a dynamic head, which is measured in meters. And it's effectively how much extra height does our pump need to overcome to push that liquid. So I think what the best thing to do at this point is not worry about this case study here, but just go step by step through the example in the notes. And then have a look at topic 3. Topic 4, template for generating pump data. In topic 4, there's a spreadsheet called template for generating pump data, and that allows you to go through the calculations step by step. So if you do that during the week, what we're going to do in the tutorial next week is go through our tutorial task, stepping through that spreadsheet. So what you need to do is just get comfortable with that spreadsheet and the concepts, and then we'll go through the tutorial task or a similar one next week. That's due on the 22nd. I'll push that back a little bit to the 25th. And that will allow you to use what you've done in the tute to help you with that task. And you'll see it's relatively straightforward, but really, really, I'm going to say it's awesome. I'll just change that due date to the 25th. Yeah, so that tutorial task now due on the 25th of August, and we're going to step by step go through that spreadsheet next week. But to do that, you're really going to have to get stuck in to those notes, topic 3 and even topic 4. Topic 4 is relatively short, but it'll all make that extremely clear too when we go through it. Does that sound good? So everyone is tasked with the task of going through topic 3 and topic 4 for next week, and we'll step through that tutorial task in class next week. That's what we're going to achieve next week, and then we'll introduce binary refrigeration systems at that point. Does anyone have any questions about that? How good is this field trip going to be? Just quietly. So I'll put the details about the first day of the field trip up to get you as excited as I am. But please do topic 3, topic 4 before next week, and we'll step through that tutorial task too and see how that applies to our case study. Yeah, good. Thanks for jumping on.